Let's discuss a question from radiation. This is from heat transfer. Okay, so what is given is basically how the emissive power varies with frequency. Generally it is how emissive power varies with wavelength will be given, but in this problem how emissive power varies with frequency. So remember, this is your frequency of the star. How to convert this frequency into wavelength? Well, if you recall that all these by Einstein and by other scientists, these stars have dual nature, or the light they emit have dual nature. Basically the light they emit has dual nature means you can understand in a particle way as well as in a wavelength way. But relating both concepts, if you go by the wave nature, the lambda, which is the wavelength, into the frequency of excitation of the star, frequency of that excitation and frequency of the wave emitted by the star, the product of that has to be the speed of light. Okay, so lambda into f is speed of light. Now lambda is something which we need to find out, and the corresponding maximum frequency which is given as 4.4 into 10 power 14. Don't forget this 14, though it is written far away, is equal to the speed of light is 3 into 10 power 8. Okay, so lambda is something which corresponds to that 4.4, and it's a wavelength. So what we get is, so if I calculate this I get 0.68 into 10 power minus 6 meters, and this 10 power minus 6 meters I am writing micrometer. Okay, that is 10 power nanometer, that is 10 power minus 6. Okay, so I get the lambda here. Now this spectral distribution of power emitted by black body, the star you can consider as a black body. So now we can apply this lambda t is equal to Weber constant, and if you recall this constant, now this is, what does this signify is that if lambda is the wavelength corresponding to the peak emissive power, and that's what it is here, that into the temperature of the star, this together is a constant, and that constant is the Weber constant, 2897.6 micrometer Kelvin. So we need to get the temperature of the star. So this is the ideal equation which we need to use. The 0.68 is the wavelength. So at this wavelength, if the star is emitting the wavelength corresponding to this range 0.68, then what is the temperature of the star? So that can be, so this is a very useful relation. Once you know the temperature of the star, you will get the wavelength. Once you get the temperature of the star, obviously it will be emitting it will be emitting power in a band of wavelength, but the peak wavelength is something which you can get from this relation. So the peak wavelength, that is the wavelength at which the peak emissive power is distributed, so that wavelength into the temperature, that remains constant always. So this is very, very important Weber equation. 0.68 into temperature is 2897.6, and therefore the temperature is 2897.6 by 0.68. So this comes out to be 4268 Kelvin. So 4268 Kelvin, the answer is B. Thank you.